Okay, let's have a sample problem. A precast concrete pile, 12 inches by 12 inches in cross-section, is driven by a hammer, given with this value for our parameters. So we try to estimate the allowable pile capacity of the pile by modified EN engineering use formula. We use factor of safety equal to 6. In Danish formula, use factor of safety is equal to 4. So basically, with the EN formula, this is the equation to compute for our Qs of U. So we simply have to get first the weight of pile plus the cup. So we are given with our cross-sectional area, 12 by 12. We try to convert that into feet times the length of the pile, which is 80, times the unit weight of the pile, then plus the cup, which is 550. This is pounds. Then we try to have the value for this, which is 1,550 pounds or 12.55 kips. And we are going to have our Q sub U, wherein our W sub RH is equal to 30 kips feet. So therefore, our Qs of U is equal to, we simply have to substitute to this equation. We simply have Qs of U is 607 kips. If we're going to get the allowable pile capacity, Qs of U all over Fs, so that is 101 kips. So using the Danish formula, Qs of U is the ultimate pile capacity is equal to this equation. So our A sub P, I'll try to use 3 times 10 to the 6 pounds per square inches. And you simply have to substitute the given values for these parameters. Then our Q sub U, simplifying this one, is 417 kips. And our allowable pile capacity now is 104 kips. Then we move on now to pile capacity for vibration-driven piles. So basically, vibration-driven piles, those are piles that is being driven into the ground by vibratory hammers. So for the centrifugal driving force, this is the equation, which is M, total eccentric rotating mass, times distance between the center of each rotating mass and the center of the rotation, times operating circular frequency raised to the second. So the vibratory pile drivers are, of course, they are patented. Some example are given or under Bodin resonant driver. And if we're going to have the, it was Davison who provided a relationship for estimating the ultimate pile capacity in granular soil. So the ultimate pile capacity in granular soil for SI units, this is the formula that you're going to use. And for English unit, for our Q sub U, this is the equation. And of course, H of P is the horsepower delivered to the pile. This one is the final rate of the pile penetration. This is our loss factor and our frequency, which is in hertz. So the loss factor SL for various types of granular soil is as follows. So they have here the value for closed-end pipe piles. This is according to bowls. So we have the value for loose sand, medium dense sand, and dense sand. So for each pile, you have now the value for loose sand, medium dense sand, and dense sand. So according to bowls, this is the formula for Q sub U. So our F sub C is the centrifugal force. This one is our WB, bias weight. This is our V sub P, which is the final rate of pile penetration. C is the speed of light, which is equal to this value. OCR is over consolidation ratio. Our L sub E is the embedded length of pile. L is our pile length. So we have here a sample problem. Consider a 20 meters long steel pile driven by Bodin resonant driver. So we're given with this HP 310 by 125 in a medium dense sand. So HP is 350 horsepower, V sub P is 0.0016 meter per second, and F is 115 hertz. we're going to calculate the ultimate pile capacity. So our case of U is equal to this equation. So for an H pile in medium sand, based on our given data according to Bowles, SL is 0.762 times 10 to the negative 3 meter per cycle. So if we try to substitute the given values, so our case of U is equal to 2,928 kilonewton. So we move on now to negative skin friction. Negative skin friction is a downward drag force exerted on a pile by the soil surrounding it. Such a force can exist under the following conditions. So those conditions is: 1. If a field of clay soil is placed over granular soil layer into which a pile is driven, the field will gradually consolidate. So the consolidation process will exert a downward drag force on the pile. So during the period of consolidation. So this is an illustration for our clay type soil that has driven over a granular soil. So this is our downward drag force, which is our negative skin friction. So if a field of granular soil is placed over a layer of soft clay, so it will induce the process of consolidation in the clay layer and thus exert a downward drag on the pile. So this is an illustration for us for the negative skin friction. The pile is driven into a soft clay type soil. Lowering the water table will increase the vertical effective stress on the soil at any depth, which will induce consolidation settlement in clay. If a pile is located in the clay layer, it will be subjected to a downward drag force. So, of course, our F sub n is equal to this equation. This is for a clay field over granular soil. So, our F sub n is equal to this expression. K prime is earth pressure coefficient, which is equal to this 1 minus sine phi prime. This is our vertical effective stress at any depth z. This is our effective unit weight of field, and the soil pile friction angle, which is approximately 0.5 to 0.7 of the angle of friction. So the total downward drag force on a pile is equal to this equation, wherein our h of f is the height of the field. So if the field is above the water table, the effective unit weight should be replaced by the moist unit weight. So we have now for a granular soil field over clay, which is shown in this figure B. In that case, the evidence indicates that the negative skin stress on the pile may exist from Z to 0 to Z is equal to L1, which is referred to the neutral depth. So for this one, this is from Z to L1. This is our neutral depth. So therefore, you have your neutral plane. So the neutral depth may be given according to Bowles. This is the equation to solve for the neutral depth, which is L sub 1. So our gamma f prime and gamma sub prime is the effective unit weight of the field and the underlying clay layer, respectively. So for end-bearing pile, the neutral depth may be assumed to be located at the pile tip. L1 is equal to L minus H of F. So once the value of L1 is determined, the downward drag force is obtained in the following manner. So you're going to compute for the unit negative skin friction, which is F sub n at any depth Z, which is equal to 0 to Z to L1. So our K prime is 1 minus sine phi prime, vertical stress equal to this equation, and small delta prime is 0.52 negative 0.5 minus 0.7 phi prime. So our total downward drag force is equal to this equation. So we have here the illustration for the negative skin friction on pile in a certain place outside the Philippines, of course. So we have here the estimated quantities based on the soil profile and the pile given in the figure for this one. And therefore, the maximum downward drag force on the pile can be estimated since in that case the pile is a point-bearing pile. The magnitude of L1 is 27 meters, and our Qs of N is equal to this equation. So if we try to substitute the given values here, those values, if we try to substitute, we get the total downward drag force is 2,348 kilonewton. So the measured value of the maximum Qs of N was about 2,500 kilonewton, which is a good agreement with the calculated value. So we have here a sample problem. So in the figure, we let h of f equal to 2 meters. The pile is circular in cross-section with a diameter of 0.305 meters. For the field that is above the water table, y sub f is 16 kilonewton per cubic meter and phi prime is 32 degrees. Determine the total drag force and use small delta prime equal to 0.6 of phi prime. So we try to make use of this equation. Our P is equal to this. This is the perimeter. We have K prime, which is equal to 0.47, small delta prime, 0.6 of the angle of friction equal to 19.2 degrees. So therefore, our total drag force, substitute these values that we have computed, is equal to 5.02 kilonewton. Now move on to group efficiency. So in most cases, piles are used in groups. So as shown in our figure, to transmit the structural load to the soil, a pile cap is constructed over group pile. The cap can be in contact with the ground, as in most cases, as well or well above the ground, as in the case of the offshore platforms. So the efficiency of the load-bearing capacity for group pile can be defined. So this is the efficiency for group pile, which is equal to ultimate load-bearing capacity of the group pile over the ultimate summation of the ultimate bearing capacity of each pile without the group effect. So this is the illustration showing to us the group pile. Group pile having a pile cap. So this is the cross section of this is the plan for our group pile. So this one are the illustration for the placement of our pile. So we have to take note, this is our B sub G, and of course this one is our L sub G. And L sub G is N1 minus 1 times D plus 2 times D over 2, and B sub G is N2 minus 1 times D plus 2 times D over 2. So for the number of piles in group, it should be equal to N1 times N sub 2. And we have to take note that L sub G here is greater than or equal to B sub G. So similarly, for each pile acting individually, our Q sub U is P times L times F sub AB. Our P is the perimeter of the cross-section of each pile. So our eta, which is equal to this equation, and our Q sub G equal to this formula. If the center to center spacing D is large enough, our eta is greater than 1. In that case, the pile will behave as individual pile. So in that practice, if N is smaller than 1, then our value for Q sub G is equal to this expression. When eta is greater than or equal to 1, our Q sub G is equal to this equation. So we have here the table showing to us the equation for group efficiency of friction piles. So this is a figure showing to us a variation of efficiency of piles in sand. So this is the ratio between D over capital D with respect to group efficiency. So the group efficiency And for a 3 by 3 group pile is sand.